Okay, so in this video I'm going to be talking about EMF and internal resistance and how those will affect your circuit. So first of all, let's clarify what we're talking about here. So EMF is a measure of how much energy is given to each coulomb of charge by whatever power source you're using, be it a battery, power pack, whatever. So it's essentially the maximum amount of energy that that power source is capable of giving. And that will be a fixed value for a certain power source. So a battery will have an EMF of 6 volts, very commonly you'll see, for instance. So that's, because it's measured in energy per charge, that's where the unit of volt comes from. So there's something else that's slightly different called terminal voltage, or sometimes just voltage for short. So this is the amount of the energy that the charges have when they actually come out of the battery terminal. So what's going to happen between the two, so the battery will give them some energy, but they'll actually lose some of that energy before they even leave the battery. So that's why we get a difference between EMF and terminal voltage. And when you connect a voltmeter, say for instance on this power pack between the terminals, what you measure is terminal voltage. So when you're not measuring EMF, you're measuring terminal voltage, so it's already lost some energy by that point. So like I was saying, the reason it's lost some energy is because there's something called internal resistance. So there's sources of energy loss inside your battery that we model as a resistor. And you'll very often see it like this, and I put them in a dotted box to say, this is actually your whole battery, and these are the terminals of your battery. So you can see it would have already lost some potential difference before it even reaches your circuit, or the terminals to go to your circuit. So we can actually think about how much it's going to lose. So internal resistance, we usually give the symbol little r. So if we measure the current in our circuit with an ammeter, what we can do is work out how much potential difference you've lost across your internal resistance by multiplying the internal resistance by the current. That would tell you how much you've lost across the internal resistance. The potential difference across this one would be given by doing the current times the resistance of this one. So I call that big R. It's often called the external resistance or load resistance. So we can see that one there. And if we apply Kirchhoff's voltage series law, what we can see is that the potential difference across here plus the potential difference across here must be equal to the total EMF of the battery, which is where you get an equation like this. So EMF is equal to I times big R plus I times small r. That's where that equation comes from. Now, like I was saying earlier, the terminal voltage is the EMF minus the amount it's lost across this internal resistor here. So terminal voltage is EMF minus the amount is lost across internal resistance, and I've realized I've actually made an error here. That should be I times little r, not I times big R, because this is an expression for how much energy is lost across the internal resistance. Be careful with that one, don't make the same mistake as me. Okay, so that's the general idea. So we know this is going to be a source of error in our circuit, so how can we actually account for this and not let it affect our measurements? Okay, so before we can start thinking about how we can employ some strategies to minimize the effect of internal resistance, we first need to think about what effect it would actually have. So if we have a circuit like this, if there was no internal resistance, the current should just be the EMF divided by the external resistance. That would give us a value. So if there is an internal resistance, what that's going to cause to happen is your value of current will decrease because you've added more resistance into your circuit. So you measure a lower current than you think you should, or theoretically you should. You will also measure a smaller potential difference here because it's already lost some potential difference from the EMF from the internal resistance there. So both your V and your I value, or A values, should be smaller with internal resistance compared to without an internal resistance. So that's how it will affect your results. So the strategies you need to take are essentially a way of minimizing that. So if you want to minimize the potential difference across here, what you can do is use very low currents, because the smaller the current, the smaller the potential difference will be across here, and therefore the smaller the error will be in your results. So that's one of your strategies that you can use there. The other thing you can do is actually carry out an experiment to measure what your internal resistance is, and that's one of the required practicals in this course, is actually measuring the internal resistance, because once you know what it is, it will be a systematic type error in your results, and you can account for it, so it's not a source of error. So those are your two possible ways of dealing with it there. So I just spoke about the systematic error, so let's define what that is. So it's a type of error that takes a fixed or predictable value. So internal resistance will be the same value every time. So it's predictable, and so you can account for it. And that process of accounting for it is called calibration. So when you take into account the fact that there's an error there. And you can only do that with systematic type errors. The other type of error is a random type error. This is when the error takes unpredictable values that change every time, so you never know how it's going to affect your results. So you can't calibrate for it because you don't know what it is. So you have to think of other strategies for dealing with those types of errors. Okay, so that's one type of error in your circuitry. Let's have a look at a few more. So an example of a random type error in circuits is called the heating effect. So in one of my previous videos I talked about how if a resistor gets hot, that its resistance will actually change. And because you're not measuring it, you can't take account of the fact that that's happening. So that would randomly affect your results, or unpredictably affect your results in a way you're not able to measure or quantify. So that would be a random type error. So you can't calibrate for it, but there are a few things you can do to reduce it. So essentially what you want to do is stop your resistor getting hot. So there's two ways of doing that. You could keep the current low, so it's actually not dissipating that much thermal energy, or you can have a switch in your circuit, so you're turning off between readings, so you're minimizing the amount of energy it's actually transferring, so you should keep the temperature down. So those are your two strategies for dealing with the heating effect, which is a random type error. There are a few others, but they're not as significant, so they won't have as big an impact. So a voltmeter, in order for it to not affect your circuit, is assumed to be infinite resistance. Because what we want to assume is that no current goes round through the voltmeter, all the current goes through here as normal. However, most of them are about 1 megaohm, which seems really big, and it is, but once you start getting into the later on stuff, looking at capacitors, where you are dealing with resistances with this sort of scale as well, this will have a significant impact on your circuit. But because it's a predictable type error, that will be a systematic type error. Ammeters, in order to not affect your circuit, would have to have zero resistance, because essentially we don't want to add any more resistance in our series loop. However, most of them are about 0.5 ohms. So in the scope of the circuit you're using, this might be a significant contribution to the error in your experiment. And again, it's a systematic type error, so you can account for it in your circuit. So you can calibrate your measurements to take account for it. The last one I'm going to talk to you about is called terminal resistance. So the terminals, for instance, on a battery, let me just grab one for you. Okay, so the terminals are these parts here. So whenever you plug a wire into one of these, there's always going to be something called contact resistance, because your connections are unlikely to be perfect. There's both going to be air gaps and stuff like that. So that's going to add onto the resistance in your circuit. Now, when you plug in wires at a separate time or change configurations, the terminal resistance will actually change because you've actually changed the connection. And this isn't something you can really measure or quantify, so this would be a random type error. So there's not that much you can do about this apart from minimizing the number of connections you have in your circuit. But obviously we need to make some connections, otherwise we haven't built a circuit and the whole thing is pointless. But it is something that's there, and it's something to be aware of going on. Okay, so that concludes the video on this one. So what follows on from this would be carrying out a practical where you measure EMF and measure internal resistance. But I won't spoil the surprise of that one, and you can find out those for yourself. Alright, thank you very much for watching, and this concludes my series on electricity in terms of going through the DC circuitry topics. I hope you found that useful, and please do let me know if you think I've missed anything, if you think I've made any errors in any of my videos, and thanks very much for watching.